Good morning, ladies and gentlemen. It's a true pleasure to be here, and I hope to learn more about what data and what questions you have as this day unfolds, and hopefully you get interested to play with some of the tools I brought you here. The talk is divided into three parts. One is a more motivational overview of some of the works we have done in the educational area, but also with some pointers to what might be possible in the near future. The second part is a tiny bit of theory, just given the time I have here in the talk, but hopefully you get interested to read up on some of the many formulas behind some of the algorithms, some of the technicalities of how certain tools are implemented, etc. And then finally, maybe most importantly, I wanted to leave you with some tools which you can use to start analyzing your own data. And I will be around all day, so if you have data and if you have a question, please feel free to find me, and we can look at your data. The first example in this first part of the talk is on trying to monitor and evaluate what's going on in 3D worlds. And this is work we did about 10 years ago, and back then you didn't have very extensive tracking in real-world environments. However, you had 3D virtual environments such as Active World and now Second Life, which allowed you in a very, very detailed way to track what people were doing there. And given all this data, you can then go about trying to, first of all, try to understand what kind of spatial, topical, and social navigation is going on, but then also trying to support this kind of navigation, which people do in their foraging activity, in their social networking activity, etc. Ultimately, you want to use this expertise and this knowledge to design learning environments that really work, that don't have bottlenecks, that lead to fruitful, encouraging and empowering learning expertise and environments. How many of you have used Active World technology? There's one arm, two. All right. What about Second Life? All right. How many of you have GPS-enabled devices with you? Wow, look at this difference. So there were very few arms for the first, a few more for the second, and so many more for now, actually giving you access to almost the same data which existed only in these virtual worlds 3 years ago. So let me tell you what we did for a conference, and I thought this is appropriate because you're currently attending a conference. And assume you would be tracked in a very detailed way. Your position in space would be tracked. It would even be tracked what you tweet about or what you text to each other. We would also know what kind of resources you access. In these 3D virtual worlds, you could click on web links, you could teleport. Can't really do this here, sorry. You could also find out who is in your vicinity, who is kind of able to overhear what you talk about, and then you can map this on. This particular conference I'm talking about is the We Learn 3D conference, which took place over 7 hours in a 3D virtual world in December 2002. And as you see, and I don't have a, maybe I can go over and show you here. Is the microphone on? Maybe I should stay here. Let me try to use the mouse pointer. So this is the center world. This is ground zero. This is where everybody starts. Some of you have designed online portals, so everybody would come through this portal. So you can also kind of try to make the leap to 2D websites if you like. But we are here in a 3D world. And particularly, you come in here. The first world has a number of breakout sessions and talks going on. Then you have more talks over here on interactivity and new avatars for science and guidance. And then there were 5 breakout sessions. And as you see, all these worlds are squares, just like this room is square. So again, I think you could very nicely find analogies of how to map a real-world conference. After those 5 real-world virtual world breakout sessions were over, we all came back to a closing ceremony with a real virtual firework, which was very beautifully done, and then we dispersed. What you see here now is color-coded trajectories of people in this space, and color coding happens according to the 7, actually there was 1 hour before the conference where people already gathered in the world. So altogether 8 hours of activity in this world. If you're interested to see how you actually have talks in such a world, you have a stage, you have 3 display walls. And so you see here a talk which talked about having 3D online worlds where people learn, and then having mirror worlds which kind of reflect upon what is happening in these 3D learning environments. And people gather around there, and you can enter queries and questions via chat, text, etc. The reason for having it in a virtual world was mostly depending on finances. Many classroom teachers don't have the resources to come to Vancouver, or they can't take off from actually doing their daily teaching, but this was done at a weekend day, so it's actually very doable then for teachers to join such a conference. Each world, I already mentioned, is a square, and you can then overlay the trajectories of people roaming through these environments. Whenever people just stand there, they grow these kind of idle circles, which get larger and larger over time. You can also identify what kind of buildings exist in this world. These are the greenish elements here. You can identify what teleports, what web links exist, and you can map this over time and then try to identify what actually happens in those worlds. So again, these are the different worlds with kind of screenshots of how these worlds look like, and the kind of color coding for the different activities. We then use this mapping technology in the Quest Atlantis world. How many of you are familiar with Quest Atlantis? So Sasha Barup and many of his colleagues, they developed an online learning environments, working very closely with Active World to try to get children interested in math and science and technology education after school. So they really saw this as a game. The Active World technology and Quest Atlantis was also deployed in boys and girls clubs. And some of the kids there couldn't read and write, and they kind of dragged people over because they really wanted to interact with people in those virtual environments. So I think it's a huge motivational effect also for getting children interested in all kinds of different science, math, education and activities. Now, if you have a 3D virtual environment, you don't really immediately see all the people in front of you. It's actually very hard to make sense of a 100-people team or even 20 people. You might have students which accidentally click on a teleport and they are off, and you have to kind of retrieve them again. Or you would like to understand if they really went through a certain learning experience, or if they just overheard the answer by another team and then sell it as their own. So you really want to understand what they do in these worlds and then how far they go through the learning experience you developed for them. We were also interested in group dynamics. We wanted to understand if people which stick together learn better, or if it's better if they go out and develop understanding on their own and then come back together to discuss it. So in another piece of work, we looked at spatial proximity and semantic coherence. So here you have different groups of 2 people traveling in these worlds together, and these are very specific worlds where you have a knowledge landscape depicted. And you will see a screenshot in a second. And we wanted to know when, where, and why users interact when they explore such an information space. And ultimately, this is very important for designing these information spaces because you want to, again, support spatial navigation through this spatial space, semantic or topical navigation, helping them to find certain resources, and also social navigation, helping them to understand who has what expertise. Maybe they can partner. If they have to do work in teams, you might like them to build useful teams which have complementary expertise, for instance. So here you see some of the visualization spaces. It's an visualization environment where you have different papers connected via linkages, and you also know which ones are how well cited in this environment. And then in the Active World browser, you can chat with each other. You can also click on the citation sticks here, and you get to know what paper you're looking at and when it was cited, how often. So this is a very specialized world, maybe too specialized for K-12 education. However, what you can do in these environments is you can track what people are doing. You can find out what they are talking about and in how far the topics they are dealing with correspond to the space in which they are operating. You can, of course, also, again, track their trajectories. So these are different groups trying to explore this space. And you can interlink the space and the semantic chat logs and bring them all in one interface, in one visualization. So here you have different chat sequences. You know time elapsed, so you see that they started in the middle of the world again, and then they move around in that world talking to each other. And this is one group, and you can also do look at another group where you then get to see that actually here people split off and they worked on their own and then came back together and talked with each other. In the interest of time, I just provide links to the paper here. So if you are working in environments where you would like people to explore spatial, semantic, and social navigation, you might like to look at this work and try to monitor in detail what people are trying to do and then support it in a more effective way. The second example I prepared here is an attempt to teach children an holistic understanding of science. As you might know, many classrooms have a map of the world on the wall. And this is for a good reason, even though many kids might never see all the many places on our planet. It is useful for them to have an understanding of the whole, and also to have an understanding that you now can take all kinds of different data, political data, resource data, war data, news data, Twitter data, and overlay it on that base map of the world. And we were interested to teach children the base map of science so that they can also get a better understanding of all the many topics they are learning and how they interrelate with each other. So this is actually part of the Mapping Science exhibit, which some of you might have seen in real. This is an effort over 10 years to educate the general audience so that you can map science using scientific means, using terabytes of papers, patents, grants, large-scale computing infrastructures, and advanced algorithms that scale to millions of nodes and records to get a more holistic understanding of the structure and dynamics of science. And what you also have in the exhibit are these two puzzle maps. These are SLIKE and SEEK puzzles where you have a map of the world and a map of science, and you're supposed to overlay and find the right spots for major inventions and inventors. The exhibit also travels in trains, and what you see here is an so-called illuminated diagram display where you actually see a map of the world, and overlaid here are activity patterns of different types of scientific activities, and so you can zoom into them. The illuminated diagram is actually a combination of high-resolution print, 300 dpi printouts on transparencies, glued on to either backlit projectors like here, or you can also have a large-scale printout, 3 meter by 3 meter if you have the space, and a projector, which then does the interactivity of different data overlays. So here in the attractor mode, you have a map of science, and you have this line going over it, and whenever one of the 554 sub-disciplines of science is hit by this line, then you see highlight in the map of the world who is conducting this kind of research. However, you can also use the touch panel display to select certain areas of science. And again, you will see highlight in the map of the world who is working on those topics. What are the centers of activity on that kind of science? You can click on obesity or cloning, and again, in both maps, you would get to see who's conducting this kind of research where. And then we also have some Nobel laureates, and you can see their impact on both landscapes. So it's a highly interactive display. Going back to the presentation, this was also deployed in a train. Trains are a great way to bring a lot of science quickly to many people. You have to be a little bit careful when designing such a train. Basically, nothing can be really too interesting, because then people don't go on anymore. So you basically enter the train at the end, and you come out in the front. And so if there's something which kind of creates a bottleneck, that's bad. But if you manage to do it well, then you can really communicate a lot of science to many people. And so this particular train made it to 62 cities in 7 months. So try to get a train, try to get a science train. So what we did to bring these science maps to children is we took the real maps, the real data. We didn't try to hide the data, but we overlaid watercolor paintings which you see here, to make it more tangible for children. And then, as I mentioned before, you have these puzzle pieces, and you have then a kind of slide and seek puzzle setup, where you now have to try to identify the right spots for those 18 inventors and the 18 inventions. And it's interesting to note that if you open a science technology book for children in Europe, you get a lot of European inventions and inventors. If you do this in the US, you get many US inventions, inventors. I'm not sure about Asia, but it's actually non-trivial to equally distribute and intelligently distribute these kind of inventions, inventors over the map. So it might even be hard for adults to do this correctly. We did the same for the science map. So here you have a map of the world. And again, you have the same 18 inventors and 18 inventions. And now, good luck trying to get them to the right places. So this is the installation in the Monroe County Public Library in Bloomington, Indiana. But it went to many science museums and public libraries also. We also took those science maps into classroom settings, trying to communicate to children that there are maps of the world, and you can use them to track the trajectories, for instance, of Columbus on those maps. And then there are science maps which you can use to track trajectories, career trajectories of scientists over the landscape of science. And children seem to think this is just very normal, that you have those two maps and you can use them both to do very similar activities. We had very interesting discussions surrounding some of the key scientists they knew, such as Albert Einstein, who has made major contributions to multiple areas of science. So where would you put him? Would you put him in his main area of contribution, but which one is it? Do you chop him up in 3 pieces and put him in 3 areas? Do you kind of try to find the middle point of all of his contributions, but there might be no island, there might be just emptiness? So what does it actually mean to have emptiness on those maps? Very interesting. And then we tried to also find out what these children, this is the second class classroom, what they thought they might be doing in science. And one of the 7-year-olds, she stood up and she said, I want to be a nuclear physicist. And then she took her little star and put it right in that area, which was very touching. We also have a number of coloring exercises which come with the exhibit. And ideally, children get a much more holistic understanding, but also a more tangible understanding of the landscape of science. It's not as abstract and nebulous anymore, which it is for many children and adults today. I should also mention that this year's iteration of the exhibit is all on science maps for kids. This is the call for maps. The maps are in production mode right now. They are going to debut in July. So if you're interested to see how these maps which were submitted can be used in classroom settings, watch out for the news items on the release of those maps. If you ever get interested to have the maps on display at your institution, or if you know a science museum close by to you, which would benefit from having the exhibit, we're always on the lookout for good venues, but be aware it comes in big crates, and you will be very familiar with the height of loading decks, and you will have on speed dial people you might not have had on those speed dial buttons before, etc. So it's a very different enterprise. The third example, maybe very quickly, is an attempt to bring some of the tools, which you will see very soon, into classroom settings and government agencies. And I'm not equating kids and government stuff here. I think they have very different needs and very different expertise to bring to the table. But I'm not bringing these tools to another computer science department. I'm not bringing them to another ivory tower. I'm really trying to bring them into the hands of people which typically might use PowerPoint and Excel and tools like this, but they don't really do network analysis right now or burst detection, etc. And the questions which I have, and maybe you have answers, I don't have those answers right now, but I would be very interested to understand what you know about it, is how do people actually make sense of big data or small data in their daily lives? How do they use data analysis? How do they consume and interpret new and existing visualizations? Can they read network layouts? Many can't. They have never learned this in school, and they might have seen some smaller networks in the news media. But they have a very hard time if you show them a large network with a backbone and community structures. And do they use any visual analytics tools or visualizations? What do they use? What's their favorite visualization? And all this has as a goal to empower people to have fun in their life with big data and with tools, but also to then identify patterns, trends, and outliers in their own data, ideally first, but then also in other data, and then make effective arguments, really use data to have more objective decision-making skills. So what we did was to go to classroom settings and to use Google Trends, for instance, or Gapminder and Wordle to help them answer when, where, and what questions. And I typed in this morning learning and analytics, and it's kind of a shame to see learning going down, especially over Christmas. You might see this. Analytics seems to be going up. Learning analytics doesn't have enough traffic to have any trajectory yet. So it's interesting. I think these are interesting indicators. How many of you use Gapminder? All right, you might like the other ones, which didn't lift up raise their arms. You might like to explore it also. So these are visualizations which I think even children in classroom settings can understand. And they typed in hamburger and cheeseburger, and they typed in pizza versus spaghetti. So they used different examples. They did not type in learning and analytics, but I think it's interesting for them to understand that you can now start analyzing this kind of data. And I will come back how we do the introduction to tools to government agency later. All right, tiny bit of theory. So in my world, and maybe also in your world, this is the general process which we are going through. So we have a stakeholder group up here, and I will use my mouse pointer to point this out. And we do a very serious needs analysis with them. We would need to understand what do they get hired for, what do they get fired for. So we really want to understand what drives them and what makes them most productive, and what are the priorities in what they need to understand. Next, we need to understand what data they have. If they don't have any data, we can't help them analyze this data or visualize this data. If they have no data, we might be able to help them to set up a process, online forms for instance, that gets them the data that after a few years of data acquisition, you can then use to acquire certain insights. All right, let's assume we have a stakeholder group which actually has data. Then it would be a matter of setting up a certain workflow that helps them analyze this data and visualize it. So here you would go from data acquisition. So you try to get your hands on the best data out there, highest quality, highest coverage, as much data as your budget allows, and also resources. There's always time involvement also to actually get access to data. Then you would pre-process this data. You would clean it, you would unify it, you would interlink it with other data, you would geocode if you want geomaps. You might like to extract networks if this is relevant for the questions your stakeholders have. So this is all pre-processing. And to be honest, you will spend about 80% of the entire project time on just this, so just pre-processing. So if you don't like cleaning data, go somewhere else. It's just what it is. You have to clean that data, because if you don't clean it, everything else is not going to be very meaningful. Next, you would do some data mining. Could be very simple. Might be just extracting a backbone for your network, or doing simple trend detection. So looking for sudden increases in usage frequency in words, keywords used in your data. Email streams, Twitter streams. You have one keyword, LAK 12, and you want to know what bursts of activity exist in that stream. And then you want to lay out your plot, your network, your geomap, etc. So this is all very serial. So you have data, you do something to the data, you have more data, you have additional columns, you might have cleaner data, etc. So it's very, very serial. And then you encounter something that is inherently parallel, and that's why it's so hard. And this is the design of visualizations that are meaningful and that are easy to use and simple. And here you would have these different steps. One is that you have to find out what kind of reference system can your stakeholders read. Timelines are good, scatter plots are good, geomaps are good, because you have learned this in school. Networks are tricky. You have not learned to read those in school. So be careful what you use here. Circular layouts are also, I believe, very tricky for people to read. Next, you might need to do projections, distortions. So if you have a 3D map, for instance, of the world, you oftentimes don't want to give them a globe, but you want to give them a 2D map. So you have to find a projection that projects your 3D surface of a sphere onto 2D. So that's one projection, and you could go for equal area maps or distance preserving maps, etc. So that very much depends on your insight need. In scatter plots, you might like to have a logarithmic scale. That's also a different type of projection distortion. In the third layer here, you overlay your raw data on the geomap, in the scatter plot, etc. And this will show you certain density patterns and will give you a first feel of your data. If you have a timeline and there is just nothing for a few years, you will immediately know that you're missing data, and you have to go back to your stakeholders, get the new data, go through all the analysis again, and then go on in your visualization efforts. The next layer here is graphic design. This is where all the color, shape, size, and other coding happens. So ideally you have a graphic designer there, or an art student or artist, who helps you to not only identify the best type fonts, but also good color schemes, etc. Oftentimes your data is large, so you need to aggregate and cluster it. And again, you could do this via color coding, or you introduce additional graphic elements such as boundaries which go around certain clusters which you have in your data. In many cases, you want to have different views of your data. You could use small multiples, small views of your data, many different ones of them, just giving you quick profiles of your data. Or you might have just 3 windows into your data. One might be a quick timeline, one might be a geomap and a science map. And ideally, these are coupled windows, so that if you click on any item, any record in the timeline, for instance, it would also highlight in the geomap and in the topical map. Next, you would like to most likely interact with your data. You want to search, you want to filter, you want to retrieve details on demand, you want to click on that record and actually end up in front of the tweet or in front of the blog entry or in front of the course syllabi of that one course. In many cases, then, you also want a legend. You want to have a title for your visualization. You want to have information on what kind of size and shape and color coding you did. You might not have to sign your maps in blood, but you might like to leave some indication of who did this map so that they can complain or provide advice or ask you to consult for them and make money, etc. So find a way that they can get back to you, especially. Actually, you should only put stuff out which you're proud of. If you're not proud of, then you might be more tempted not to put your name on it. But just do visualizations that matter to you and to your stakeholders and proudly sign them, just like the old map makers all signed their maps. And finally, deployment. As you might realize, it makes a huge difference if you are designing for a handheld device with very small number of pixels, or for a large display wall, which might be as large as that entire wall over there, or design for printouts on paper, which have much higher print resolution quality, and you can pack a lot more information in a square meter than you could possibly do it even with the best, highest resolution monitors out there. Now the problem is, depending on what you select, for instance, for deployment, you might not be able to pack so much data, you might not be able to have certain interactivity, you might not be able to have certain types of interactivity. So this all interacts, and if you have designed visualizations, it's very healthy to actually start dissecting them and trying to figure out what you did in every single step of your process. And ultimately, you're also now using results from, for instance, your analysis process and you use clustering results, which you did down here, in your aggregation clustering step. So there's also a tight coupling between what you do in the analysis phase and the visualization phase. And ultimately, you bring back your really impressive visualization to your stakeholders, and they might have no idea what this is, or they have no use for it in their daily lives. So it's very much a very iterative cycle here. When I started doing this research, the different types of algorithms which you need to make it through workflows that potentially have 12 different algorithms involved. These algorithms, they're written in C, in Fortran, in Java, and you name it. In many cases, the output of one algorithm doesn't fit the input format of the next algorithm. So if you use 12 algorithms, you might have 12 minus 1, 11 converters in between all of those algorithms, making it very, very time-consuming to make it through this once. And then it's not much easier and faster to make it to a good visualization. So we started to do tools which basically support different types of analysis. So one type of analysis is statistical analysis and profiling. Another type of analysis is temporal analysis, really answering when questions. Then there is geospatial analysis, which helps you to answer where questions, so where do things happen. And there's also topical analysis, aiming to answer what questions, and network analysis, with whom questions. These types of questions occur at different levels. They might occur at the micro level, so just single individuals and their career trajectories, for instance, or one student and the many courses he or she takes, and where he or she is coming from and what she's going to do next in her career or his career. It might be at the meso level or local level, an entire department and all their teaching and how it relates to other teaching on campus, for instance. And at the global level, looking at education in a global sense, and I think that is more and more necessary today, where you have brain drains all around the globe and also reversing ones. So here I don't have examples for you which come directly out of the education domain. Instead, I have examples of science, technology, structure and dynamics studies. And hopefully you can make the leap to some of the data you might have. So in one study, we were asked to identify and map Indiana's intellectual space. So this is Bloomington, Indiana, where Indiana University is. Indianapolis, where the airport is, and then Lafayette, where Purdue University is. And in this particular case, we had proposal and funding data for the state of Indiana in the biomedical domain, and covering industry-academic relationships. So every single proposal had to have industry and academic partners. You can use this data set to identify pockets of innovation, so where do new ideas get born, and then also how do those ideas make it into products. And ultimately, our clients also wanted to understand the interplay of industry and academia. And so here the color coding used is very simple. You have red for academic and yellow for industry, and then academic to academic is connected via red linkages, and academic industry via orange, because that's the mixture color of red and yellow, and then industry is yellow. And this was a flash animation which you could animate over time. You could click into certain nodes. You could get to see the listing of all the proposals and all the awarded grants. You could sort it by lead PI. You can sort it by dollar amount requested or awarded, etc. I believe you can do similar maps for some of the data you might have in terms of students and how they go from one institution to the next, in terms of research that gets conducted in the education domain, and I have some of those maps later on for you, and also in terms of industry-academic partnerships that already exist in your emerging space. What you can also do is to animate these kind of networks. So here you have a network of information visualization researchers. It covers one conference out of 3, no books, no journals. Each node here represents a researcher, so each node is labeled by the last name of this researcher. And as time goes on, you see nodes grow as people publish more and more papers. And actually for the LAK conference, I highly recommend that you keep good track of all these papers and animate them to your 10th anniversary in a similar fashion. And you also get to see that we did some color coding here according to the number of citations received. So what you want is a large node which is dark, highly cited. You also see that there are some nodes which are large and not very dark. And it could be that these people published and nobody cared, or it could be that they recently published a lot, like John Stasko here at Georgia Tech, who is one of my heroes. He was just really productive very recently, and really nobody had a chance to cite those papers. You also see that many of those networks are unconnected. For instance, here Virginia Tech is very much on its own. Berkeley is on its own, etc. And this is very normal because oftentimes researchers work with their student sets, and if they have a many author paper, it's a fully connected clique. And then you have some weak linkages, like Stephen Ike worked at Xerox PARC and CMU. And you see that networks that grow in research labs, such as Xerox PARC and Ed Robertson and Stu Card and Jack McKinley, for most of what this data set captures, actually work together in this environment. This doesn't happen at a university. Typically, each university has exactly one information visualization researcher. And that researcher, like Ben Schneiderman, would work with an incoming, outgoing stream of students. And what is also interesting then to understand is really how these networks evolve over time. And again, I think it's interesting not only to do this for publication data, but also for funding data. So who is co-PIing with whom? To do this for patent data, who has patents with whom, and so on. In another piece of work, we wanted to understand the impact of the internet on the importance of space. So does space still matter in the internet age? Do you still have to be at MIT, Harvard, etc., to do most impactful work and be connected to the right crowd of people, etc.? And so what we used here is a 20-year data set of PNAS publications. So it's mostly biomedical publications. And here you see a map of the US, and these citation sticks indicate how many citations go to what institution. So Harvard clearly sticks out of the crowd with enormous number of citations to its work. What you see down in the lower right is maybe more relevant for answering the questions. Here you have plotted the log over the geographic distance on the x-axis and the log of the number of institutions citing each other on the y-axis. And I would have expected that as the internet comes into existence, this curve would flatten. You would actually see more institutions citing over longer distances. What seems to happen, however, is that the curve gets steeper and steeper as time passes. And we didn't really have a good explanation, but Barry Wellman, who gave the keynote yesterday, and a colleague of mine, Howard White at Drexel University, they, around the same time, published work where they also looked at a similar phenomenon. And they concluded that as we are bombarded with more and more information, we actually use our social networks, our scholarly networks, in a more extensive way to also help us decide what should be listed in the list of references at the end of your paper. And ultimately, we also maybe take into account whom we have to face in the hallway again, or at the next conference, and that might also have some impact. So we might read more, but the citations are not more global yet. In recent work, we work very closely with funding agencies. Here, the National Institutes of Health, and we look at the, you could almost call it return on investment, but it's not totally correct. So here you have data where you have funding data, but also publication data, and both are linked. So NSF and NIH now have found a way to interlink the funding they give out to the publications that acknowledge that funding. And what you can then do is you can look at our one investigator-initiated research, for instance, here on the left-hand side, and you can look also at large center funding, and all this funding which you see here is on tobacco research centers, kind of same time frame of funding, not exactly the same dollar amount. You have this little graph up here, but same topic areas. And you see that the networks that evolve out of the center funding look very, very different compared to those which come from the R1 investigator-initiated research. So these are publication co-authorship networks, and different R1s have different colors here. And similarly here, different centers have different colors. So very different structures. And if you're interested in fast information diffusion, then obviously a network which is denser connected and more holistically connected is more easy to diffuse information in than a network that is highly dispersed. In other work, we look at topical trends. So here we use the same 20-year PNAS data set I mentioned before to identify 50 terms that are widely used and that also experience a sudden increase in usage frequency in those 20 years. And we did this only for the top 10% most highly cited publications. So here each node represents one of those 50 terms and is labeled by it. The circle size corresponds to the burst weight, how sudden an increase of usage frequency that term experienced. The circle color is the burst onset, the year in which that burst came into existence. And the ring color is the year of the maximum word count. Given the color code on the right-hand side, you also get to see that the greener, lighter yellow colors are earlier years, and the red and black colors are the later years. And you see that typically you have the burst first and then the widespread usage. And it would be really interesting to now fold in the years 2002 to 2010, for instance, or 2011 if you have the complete data yet, and see if really growth and protein and models have been experiencing wide stream usage. And I think there is a certain prediction and predictability in this kind of work. So I think there is normal science which can be predicted to a certain degree, and then there are revolutions in science and external events and stimulus funding and so on, which is much harder to predict. If you got interested to have more information on the algorithms applied and the formulas behind this kind of research, there are a number of special issues, but also books now out which help you to understand the mathematics and the computer science behind this work. Practice. So this is the main part where I would like you to understand that you can map your own data. This is the cover which we proposed to ACM when they asked us about suggestions. And they didn't go for it, but I think it's still very telling and it's characteristic for these tools which you're going to see. You might be familiar with tools where somebody else figured out what you're supposed to eat or use. So tools like this are, for instance, Photoshop or Microsoft Word or web browsers you might be using. Somebody else figured out what's in that menu system, and then you're just using a subset of all the many possibilities which these tools offer to you. What I have here for you is a tool where you go basically to a China buffet-like environment, and you go to the first tray or plate, and you pick some of the most delicious-looking data readers. And these are readers which read in your data. So this could be Excel files or network formats, etc. These are the data readers which you need in order to get your data into that tool. Could also be a database connection if you have a database on campus or in your company which you want to connect to. Next, you go a little bit over, and there are all these deliciously prepared data cleaning things. I already mentioned that 80% of your time is going to be spent on that tray, on those algorithms, on that activity. So you pick some of those unification algorithms which give you latitude, longitude if you give them an address string, other algorithms which help you to extract networks, etc. Then you go to the next tray, and you might like to get some network analysis, modeling, visualization tools, Or you're more into temporal analysis, so you get John Kleinberg's burst detection algorithm or any of the other cool, neat new algorithms that are out there. And then, of course, you might also like to communicate results to diverse stakeholders. So you grab a few of the tools, the visualization tools, which are in the kind of right-hand corner. And you might also be interested to save some of the visualizations or some of the data sets out. So again, there's a tray for data writers. And so you basically cherry pick your favorite algorithms. You put them in the so-called plugin directory. And when you start the tool, they all end up in your menu system. And by the way, welcome to this brave new world where every morning when you can come to your office, you will see new data sets, new algorithms, new workflows that other people have created for their own purposes, maybe not with you in mind. But you will have a chance every morning to select some of them. Just like in some cases you might go to Twitter or to Flickr or to YouTube to get some of those resources. So what we are doing here is to help scientists to design their own dream tools. And as you know, even Galileo Galilei, he grinded his own lenses because nobody else was doing it for them. And it was the same for me. Nobody else gave me these kind of tools, so I had to build them myself with a lot of help actually through industry standards and lots of programmers involved. And I will tell a little bit more about this later. But it's really a matter of taking what exists, repurposing it, extending it, and inventing hardware and software that you need ultimately for your dream come true tool. So you might wonder, what are macroscopes? So you already heard a little bit about the plug and play, but what about this macroscope business? So many of you might be familiar or maybe even own a microscope and a telescope. And as you know, in former times, there have been researchers which used the same microscope or the same telescope for even their entire career or at least a major chunk of their career. And then maybe they got a new one, and that was way better than the old one, so they used this. But it was a very static instrument. What I'm proclaiming here exists, and you will have to just face it, is an environment where you have very flexible so-called macroscopes which help you to make sense of processes and data sets that are either too great, too slow, or complex for the human eye and mind to understand. And these macroscopes evolve on a daily basis. And if you proclaim something like this to arts and humanities scholars, they don't want this. They just want a tool which they can become very familiar with. They have their data, which they know very well, and they just bring those two together and work with this. But I don't think this is reality anymore. I think you have to get to the point that you embrace this new technology and you embrace new data and you become a data junkie and you become really interested to try out new toys, basically, new tools, and have fun with them. And so, again, these macroscopes, which I'm trying to get you interested here, are continuously changing bundles of software plugins. And you might sort some old plugins out because they don't do so well, or they're too slow, or they don't work with the data you really want to analyze. But you might also hire a programmer or two on an hourly basis because you need that one more data reader, or there is this new algorithm and somebody coded it up, but it's not fast enough, so you really need it faster. So it's a very flexible way that millions of people can actually do small bits and pieces, and then if they share those plugins, it becomes something very powerful. And ultimately, just like you share images and videos via Flickr and YouTube, you can now also share algorithms via this kind of infrastructure. And to be honest, assembling a new tool is really as fast as collecting your new music library. And I think many of you are very familiar in how to do that. And so to give you another kind of food metaphor here, and you actually have these round tables here, and in some places you actually have tables here where you have people from different areas of science or from government and industry and academia sitting around this table, and they all typically have their own view of this world. They have different, for instance, in network science, in the study of networks. You would have social scientists, which really see the world in matrices. You have scientometricians like me, information scientists like me, which see it as a node list and an edge list. And then you have physicists, which just are happy to have an edge list because they're very interested, for instance, to understand universal laws, and that's all they need there. They, for instance, would like to find out if this network has a power law characteristic, and this is the data they would read there typically. So similarly, here around this table, you have people which typically cannot share their algorithms and their data readers and writers, etc. And so it's sad. And by the way, there are some women involved. So what we tried to do is to create an infrastructure where you can plug and play data sets and algorithms. And we went through a number of iterations of the core, which then lets you plug and play. And after 3 attempts, we finally settled on OSGI, which is the Open Service Gateway Initiative, a big industry standard, which allows to build modular software infrastructures, which you can typically find in cars, in coffee machines, in washing machines, etc. Yeah, different ways to just modularize software. And I would argue this industry standard has cost more than NSF, NIH together could afford for building modular software designs. So we are leveraging this, and then we added a very small piece of software, which we call Cyber Infrastructure Shell, or SciShell. And that's a specification and prototype implementation that basically creates sockets into which you can plug and play data sets and algorithms. And what you then can do is you have developers, which might come from different areas of research, and they have algorithms. So typically grad students implement those algorithms in whatever language they speak, right? Fortran, C, Java. And then you have so-called wizards, which help you to get your data or your algorithm wrapped up into a jar file. And these are the jar files which you can save in that plugin directory, and then they show up in your menu system. And this is all then plugging into the SciShell itself. And then on the right-hand side, you have users, again, which are not computer scientists, and they create their different types of tools. And they start building workflows. So I already mentioned the workflow of all the data acquisition, pre-processing, analysis, layout, and then visualization, and then going back, realizing that you don't have the right data, doing it all again, etc. In many cases, the workflows are also used in teaching, so it's very important to have a wiki environment which you can use to really document in detail how this all works. And so as you see, computer scientists are really only needed to create that empty shell, just like you needed computer scientists to set up Flickr and YouTube. But when Flickr and YouTube had no content, it was totally useless for all of us. And similarly here, just the core itself is very small. It's very easy to maintain also, which makes it very possible to sustain such an effort in an academic environment. But the value comes through all these algorithm plugins. If you get interested to check out what we did there, there's a very detailed documentation on how to do a little Hello World Java application and integrate it as a plugin, how to integrate Java code itself, how to integrate non-Java code. So feel free to use this infrastructure to just organize your own code. You don't have to share with anybody if you don't want to. But some of you might actually want to share your own algorithms this way. And we have a good process in place that you can actually get citation counts for sharing. We are using the normal currency of science here. You can also go to SciShell.org and see a number of the tools which now are SciShell powered, if you wish. And the big advantage of having a SciShell powered tool is that you can take plugins from one tool and you can plug it into another tool. One of those tools is the Network Workbench, which has been downloaded by more than 110,000 people, but we unfortunately don't know what people do with it because there's no registration. You just go there, you download it for your specific environment, and you start playing with it. And there are more than 170 different algorithms now in that tool, so you can play for a while. It has been used in computational proteomics, And in the interest of time, I'm just going to mention those, but all the links to the papers are here. Computational economics, the product space work, some of you might be familiar with. Computational social science, we mapped all of the English-speaking Wikipedia using the tool, so it scales very well, and compared to Gephi or Cytoscape or other tools you might be familiar with, it has a lot of data analysis algorithms for directed but also for weighted networks, which you might be interested in. Also computational epidemics and others. The second tool I wanted to mention, which is maybe more relevant for the data you have, is the Science of Science tool, which was funded out of NSF. And here you have different network visualizations. You have these horizontal time graphs. And you also have science maps, which you can use to overlay the expertise profiles of a single person. Like, for instance, you can read in my EndNote file with all of my publications, or an institution's profile, or an entire profile of a conference, and overlay those. You can do simple geomaps, and you can also do hierarchical network analysis using Blondel, and then map these hierarchical networks using this circular hierarchy. The tool comes with extensive documentation. So I worked at NIH for months, and there are 24 hours of video documentation if you're interested. But I thought what I should use my last 2 minutes for is to really take a data set which is relevant for education. And what I did was to go to the NSF award search, where you can download all the fundings that NSF has given out. And I typed in as NSF organization DRL for Division of Research on Learning in Formal and Informal Settings. Anybody is funded from this? Can I see some hands? So you might be on the map, watch out. So there are 769 currently active awards, 891 unique PIs funded by 73 different programs. And the sum of all the awarded amount to date is about $1 billion. And this $1 billion also comes into existence because you have projects which have been starting very early, like as early as January 1st, 2002. And they are going to expire soon. But then you also have projects which just started, and they're going to go on for another 5 or longer years. The data looks like this. You have a title, you have the NSF organization, which is all DRL by design, given that I constructed the query this way. You have the different programs that fund it. You have a start and an expiration date. You have the organization, which actually is involved, and you have the awarded amount. You have an abstract where you could do very interesting topical analysis, which I didn't do here. And you have all investigators, which are listed as PI or co-PI on the award. First of all, you can map all these many grants using so-called horizontal bar graphs. So here you have a bar which has text on the left-hand side. So you see here, for instance, the title of the project. Then you have a start date and an end date, which is the expiration date here. And you have an area size that in this particular case equals the dollar amount. And you can look at this all, and you can browse through it, and you might like to find out what are the big bars, lots of money in little time, for instance, or what are the ones which are still in existence and still going strong for a number of years. So you can, first of all, map all this, and you can also, if you want, color code, for instance, by gender of lead PI, if you have that information. Or color code all those which are career awards or equipment awards, etc. Then you can also extract collaboration networks from this. So for instance, all investigators just extract the co-occurrence network of that one column which had all the investigators in it. And then visualize it using, for instance, one of the built-in visualizations or Gephi or any of your favorite tools. So here you see it's rather unconnected. And if you zoom into this area here and then kind of turn on the labels for the nodes, you get to see some of the larger networks that exist in this particular data set. You can also do bimodal networks of PI institutions to co-PI networks. And again, you have here, actually, you have a giant component and some smaller networks. And this is the giant component, and I thought you might be interested to see who is in the middle of all of this. So again, these are the institutions of the lead PI, not the institutions of all the other co-PIs, just the lead PI institutions. And then those connected to all the PIs which are listed on the entire award. And you might like to not only see the labels for the institutions, but also for those people nodes which actually are interconnecting different institutions. And again, you can also visualize this in Cytoscape or Gephi. So you can integrate entire tools as plugins. We have a new tool which is funded out of NIH, and that actually also created an OR bridge. So if you're an OR fanatic, you can use this. There are a number of European projects now which add a lot of textual analysis algorithms. And ultimately, if you are interested to create your learning analytics tool, you might like to just take an empty shell and see what readers and what processing and what analysis and visualization is relevant for your life and decision making, and then just add them into an empty shell and brand it under your own name or under learning analytics and have fun with it. Thanks so much.
Katy, thank you so much. Hopefully you are as blown away by that as I am. And the fact that this isn't just sitting in labs, this stuff is available to download now. So I know we have information visualization people here, and there's a real invitation from Katy to engage with her for the rest of today. She's around just the rest of today. We've got time for maybe one or two quick questions if somebody would like to ask anything. Otherwise, I'm picking up big let's get coffee signals. Okay. Katy, are your slides, can we get a copy of those?
Sure, yeah.
So they will go up on the LAK site.
There are also handouts here. If you just want to see all the many algorithms you now have at your disposal and some of the workflows you can use to run some of your own data, just pick up some of the handouts.
I'm looking forward to the LAK 13 InfoVis panel where we might show the Learning Analytics portal. Katy, thank you so much.
Sure, thank you.